Welcome to December 2020's Aerospace Testing Innovation Podcast, the fifth in our Testing Innovation series. We've done a lot on eVTOLs and electrification in the last few months, so this month we thought it'd be good to tackle a different topic altogether, autonomy, by interviewing Jon Damush, CEO of Iris Automation. Iris is one of, if not the, leading avionics companies developing the detect and avoid systems that will underpin the unmanned autonomous aircraft of the future, such as delivery drones and one day passenger aircraft. Without these really complex avionics systems that enable aircraft to see and get out of the way of obstacles, autonomous aircraft will not be possible. So Jon is amazingly knowledgeable about DAA. He's made it his life's work to develop the technology. So this is a really interesting chat about how it works, how it will be certificated and commercialised, and the challenges and benefits it brings. I hope you enjoy it and see you on the other side. So, detect and avoid, is that the terminology that you use to describe Iris Automation's technology?
Yeah, I mean, it's kind of the community uses detect and avoid, sense and avoid, see and avoid. You know, what is the wording that's typically codified into regulations around the world is see and avoid, because those regulations were written with the assumption that it was a human eyeball that was performing that task. So it has been interesting, especially over the last 10 years, this conversation that's been going on around the use of the word detect. Yeah. And, you know, at some level, you even get into a legal conversation about, well, is that something that satisfies C? Because C is what's codified into the rules. So we generally use detect and avoid as the terminology.
Okay, so does that cover off, you know, when you describe to someone what detect and avoid is that it really? Is that how you describe it?
Yeah, I think again, this is an evolving space, and it's a fascinating place to be. And I would actually argue that the middle A in DAA most people think is and, but actually, if you think about it, it's detect, alert, and avoid. And that's probably useful nomenclature to start using, because depending on the concepts of operation of your unpiloted system, you may or may not have an operator in the loop of command and control. Many unpiloted systems trend closer towards full autonomy. And I use the autonomy word loosely. I mean, in the truest definition of the word, there really isn't anything out there that's autonomous yet. Meaning that it's self-aware, making its own decisions based on, tasking only. Typically, when we say autonomy in the unpiloted community, we're really referring to a system that does the whole mission that it's been programmed to do, right? But it's been programmed, right? It's a very discrete system that, goes to waypoint A, then goes to waypoint B, and then loiters or whatever the mission is. So, the spectrum goes from that level of kind of autonomy all the way back to what we would refer to as remotely piloted aircraft system, or an RPAS, which has a pilot in the loop, literally with hands-on throttle and stick, and they're really using telepresence to operate the aircraft. So this is kind of the concept of operation of, say, the Predator and the Reaper class of UAVs. And in that case, you do have to detect a potential threat, alert the operator, hence the middle A, our suggestion being let's use alert nomenclature. And then the human pilot has to make a decision and then affect a change in behavior of the airplane. And then the airplane then responds to those control inputs and performs the avoid maneuver. So we don't typically, our history has been focused on smaller drones where there is not a pilot in the loop. Instead, the pilot is kind of on the loop, monitoring the pre-programmed behavior of the system, in which case what we typically do is our detectors, which is a computer vision-based camera system that has a GPU processor coupled with it. So you can think of it almost as a smart camera, but it acts as a visual detector. And what it does is it detects movement that's different than the ground, that's different than the own ship, and says this is a potential threat. And then we run through a series of machine learning algorithms to classify that moving target. Once we can classify the moving target, then we have enough information to understand the gross size of that target. And based on our knowledge of the geometry of the imaging system, we can then compute an approximate range for that target, which is really the novel bit of Iris's technology, because these are single camera systems. And single camera systems are not very good at depth estimation. So the fact that we've been able to use a single camera system to get depth is a really important feature of our capability. So our detector will do all of that work, and it will then typically alert and trigger an autopilot directly. So we're tracking targets. Once they get to a point where a near midair collision looks imminent, then we will trigger an avoidance maneuver, which, varies by autopilot and concept of operation and aircraft. But the most common is a descending right turn at the maximum turn rate and descent rate that the aircraft is capable of.
Okay, great. So can I just ask you the camera that you're talking about? I mean, so where would it be fitted on an aircraft? I'm presuming it gives you a whole 360-degree view of what situational awareness of what's going on around the aircraft, right? Is that?
Yeah, it's a great question, and the answer runs the gamut, basically. For certain applications and certain operations, you might only need a forward-looking camera,
right? Because
that's where the threat is coming from.
Mm-hmm.
More generically, it'd be better to be able to see more of a field of view. Mm-hmm. So our system is actually designed in the way that you can use one or many cameras depending on your aircraft configuration and the operation you're trying to go perform. We customize that for each and every aircraft manufacturing partner that we have. We tune it for the operators and end users that are ultimately getting the benefit of the detect and avoid because they get to go fly their operation. Mm. And the number of cameras specifically and the placement of those cameras is largely driven by the configuration of the aircraft itself, so that we maximize our field of view of the sky and minimize occlusion from aircraft structure, propellers, etc.
So what's the biggest aircraft you've used it on?
So we actually mounted it on a Piper Cub.
Okay.
To do flight testing. So there really isn't. There's not really a limitation in how big an airplane we can be on. The challenge comes on the smaller side of things because while our system is actually quite small, the compute module is the size of a stack of credit cards. And the camera itself is kind of the size of like your AirPods charging case.
Yeah.
So that's not huge,
no.
But that's still big in relative to, say, a 10-pound drone, right? So we typically don't really focus on that part of the market, but that works fine because that part of the market is typically not looking at BV loss type of use cases either. Those typically tend to be the hobby drones, the close-in photography work, maybe some real estate or roof inspection stuff that can all be done under existing drone rules around the world. In the U.S., it's Part 107. They don't really need a BV loss or a detect and avoid system because they're operating under the bubble of protection that those rules grant them. Okay. So our sweet spot is right around kind of the 30-pound drone and bigger, all the way up to piloted aircraft. Honestly,
great. Okay. The product itself, you mentioned there the size of it. Is it something that you're working with manufacturers to integrate directly into airframes, or it is?
Indeed.
Yeah. Okay.
Yeah, indeed, and that's the best way to do this.
Mm-hmm.
To date, the only people that have been allowed to fly drones for commercial use are either under rules like Part 107, which exempt the operator from type certification, or under special exemptions and waivers for type certification. Mm-hmm. But there is zero doubt that ultimately anybody that wants to operate a commercial aircraft will have to get that aircraft type certified. Mm. So what's critical about type certification, and I know this coming out of Boeing and in situ, is that you really want to lock down your aircraft configuration as early as possible in the type certification process. And, the irony is that you can actually put inert systems on aircraft and go through a type certification as long as that system does exactly what you say it does or doesn't do. And you can get your type cert basis on that, or your type cert on that basis. Mm-hmm. And then you can iterate over time and improve capabilities and add capabilities and get supplemental type certification, which is a much, much quicker and easier and less expensive path than your initial. So that puts, pressure, but for us, it's opportunity. Because we do want to integrate tightly with our manufacturing partners. We do want to make sure that when they're making design decisions around structures and, electrical wiring and, EMI, that they are aware of our system, they have all the specs of our system and can incorporate that optimally in the design of the aircraft. And now they have a baseline with a vision-based safety system on board that will grow with them through software, right? Because that's really how we improve our capabilities over time is through software.
Yeah, sure. Can I just ask you quickly about well, probably not quickly is not appropriate, but I mean safety. Is it? I mean, it's I mean. It has to be redundant, right? There's a kind of redundancy built into the system. I mean, it's such an important piece of equipment, such a key piece of equipment. This kind of system. I mean, what's been your approach to safety within the kind of technology development itself? I mean, how are you ensuring that when you put one of these on, everyone's going to be 100% confident, when you're using this?
Yeah, well, I mean, if there's one thing about flight that is true, the only 100% safe flight is no flight.
Right, okay.
So, the perfection is unobtainable. There is no such thing as 100%. To your point around, fault tolerance, fail safes, redundancies, there's certain elements of our system that are single point failure. And that's going to be true of just about every UAS in the small category. Because you just don't have enough size, weight, and power. As soon as you start to put a lot more redundancies on systems, then all of a sudden you end up with a big airplane. And now you're in a different category of aircraft, which different category of rules and, ground and air risk things. So there's this interesting pressure and dynamic that's working in the certification arena right now around how you can take systems that have single point failures, like a battery, for example, and certify them for flight. We're in the same kind of challenge area. What we do is we actually have written watchdogs into our software so that we are constantly monitoring the performance of our system. And if anything goes off nominal, then we alert. And we let the operator know that, hey, the Casia system's not performing within limits, and now based on their operational approach and their risk mitigations, they will perform some other behavior. Maybe that's hover, maybe that's land, maybe that's stop all operations, whatever the operation dictates. So that's what we do on board. I think in terms of, let me escalate that answer to the next layer. And when you think about DAA in general and not just our system, there is no such thing as a single modality that's always going to protect you from a collision, period. And that's true of manned flight today. When I go hop in a Cessna and go flying for fun, I'm but one component of that chain of safety systems that are put in place to make sure I don't trade paint with another airplane. Sure. It starts with how I plan my flight, then tactical mitigations like airspace and specific equipage and access rules, right-of-way rules, cruising altitudes, air traffic control, ADS-B, transponders, radar. All of these things are used throughout each and every flight. And then what I perform as the pilot in the seat is basically the last line of defense. If all of those other mitigations fail and there is a threat that comes within my well-clear boundary, then I have the responsibility to use my human eye-brain combination to see and avoid that traffic. Note that in doing that, there is no separation standard. There is no, you must maintain this much distance. Although within 500 feet is typically considered a near mid-air collision, and you should report that because that means other mitigations in the system have failed. But the humans there is the last line of defense, and I think it's useful to think of our system as the analog to that. When we took the human out of the cockpit in the unpiloted aviation world, we basically took the third leg of the regulatory stool, one leg being pilot, one being aircraft certification, the other one being operational approvals. And we sawed that leg off the stool. And now all of a sudden, what are we going to do, right? Like, where do we take all of those linkages and all of those redundancies that the pilot provides? And how do we incorporate that into the aviation certification and approval system? So this is what the community is wrestling with today. Our view is that what we want to do is help be the analog for that last line of defense that the human provides, because we are a visual system. So our performance in terms of visual acuity and target accuracy and range estimation is roughly comparable. But we never turn off, and we're never distracted by a GPS task or a radio call or somebody in the cockpit who's asking you a question, right? Like, our system is 100% devoted to scanning the field of view at all times. And from that perspective, I think we actually stand a chance of increasing the level of safety of aviation writ large, not just in unpiloted systems, but actually ultimately into manned systems and the UAM space as that world starts to mature.
So interesting point. I think, and similar to the automotive case as well, where you're seeing this kind of increased level of automation with driving. I mean, do you take your cues from that sector at all, or is it an entirely different use case, do you think?
No, I think there's a lot of lessons to be learned there. The good or the bad of the automotive world. It is a less stringently regulated world. I don't want to say that in a negative term. It's just, the risk factors are a little bit different than aviation.
Yeah.
So it's regulated differently.
Mm-hmm.
I think that world also has perhaps a more complex collision avoidance problem to deal with, which is interesting. So it's a slightly less regulated world and a much more complex environment where you've got, kids, dogs, balls, snow, rain, like all kinds of stuff that's just, the variability on the road is massive, which is why you see the ridiculous equipage on some of the self-driving car experiments, right? I mean, these things look like porcupines. They got stuff all over them because every time they go to try to do something, they learn of a new edge case, which requires a new sensing modality, which now requires a new piece of equipment. And, so certainly we take cues from that. But I would also say that we take cues from traditional aerospace. And if you look at the safety record of aerospace over the last 50 years, what you've seen is a remarkable increase in the level of safety of Part 121 operations, that's the FAA rule that governs airline operations. So airline operations safety record has steadily increased decade on decade since the 50s. And that's largely due to, obviously we're learning things, we're getting better in terms of operations. But when you look at the deployment of technologies that help automate the task of flying the airplane, there's a direct correlation between the global safety record and the increasing levels of automation in the cockpit. It's a really good thing because we've been able to offload the human of a myriad of tasks. It was in my lifetime that you had a flight engineer up in the front of the cockpit who was managing this gigantic board of gauges and circuit breakers for every system that was on the airliner. And now you can have one person up there while the other person's in the back getting food or, using the loo.
Yeah.
So that level of automation has really, really stepped up safety in airline ops. We're starting to see an increasing use of automation in smaller aircraft, specifically business aircraft and general aviation aircraft. And I believe you're going to see a similar uptick in safety for those communities over time as we increase automation. So, both automotive and aerospace have precedent that give us, pointers as to how to safely introduce automation in a crawl, walk, run approach towards, the ultimate goal that everybody has, which is an autonomous aircraft that as you walk up to it, you've got your app out, you say, I want to go here, and you get in, the doors close, it says, welcome aboard, fasten your seatbelts, and off you go, right?
Yeah.
Like, cool. I can't wait for that to happen. Hope it happens in my lifetime. But, the path to get there is through incremental improvements in automation to offload the human and augment what the human does really well, which is judge.
So you mentioned certification a while back, and this crawl, walk, run you just described there. Where are we on the journey with certification and regulation of this kind of a system? Are we on crawl or walk or run, or are we back?
Yeah, I think we're still in the crawl phase.
Yeah.
And I don't say that negatively. I think, this is something that for people that are new to the aerospace and the aviation world, it could be hard to understand sometimes, and it could be perceived as like, oh, well, it's just the bureaucracies around the world are just slow to adopt new technologies. But you know what? They should be. The consequences of failure in aviation are massive. You're talking about loss of life, and you could argue that, oh, come on, my 15 or 20 pound drone, that's not going to kill anybody. Well, it might. If that thing ends up in an engine nacelle, that's going to cause a real problem for somebody else. That then creates a chain of events that, that's what always leads to accidents is a chain of events. So what you're trying to do as a regulator is identify things that from the outside looking in, appear innocuous and small and like, what? Like, you're really worried about that? But when you actually analyze accidents in aviation over history, you see that things that would be relatively innocuous viewed alone actually are part of the chain that leads to an accident. So, I think the crawl is the right thing to be doing right now. That said, I actually am very pleased with how aggressive regulators around the world have been about trying to find new paths into certification for these small aircraft. It's certainly never as fast as, those of us in the Silicon Valley startup world want it to be. That's just the nature of different timelines. Mm-hmm. But that's the challenge to industry, is figure that out. Mm-hmm. The regulator, the U.S. specifically, has put into place this, what we call durability and reliability basis, means of compliance for certification. That's being done under the FAR Part 21 rule set. And what's fascinating about Part 21 in the U.S. is that's been on the books for a long, long time. So, the original authors of that rule were prescient enough to understand that ultimately there's going to be special aircraft that don't fit. Mm-hmm. And we need a part of the rules that gives the FAA the authority to certify something that doesn't fit somewhere else. So, the initial, when I was at In Situ, we put the ScanEagle aircraft into the 2117B certification path. And it's a good path. It works. What it requires, though, is what we in the engineering space refer to as the book. You need all of your documentation in ridiculous volumes with ridiculous detail and testing that's both, model-based testing, simulation testing, software in the loop, hardware in the loop, actual real-world testing that all has to be statistically significant and reinforce each other. So that's an expensive endeavor when building an airplane. What the regulators around the world have found is that, hey, actually, maybe we don't need to do that level of rigor for all of these systems that were built with commercial off-the-shelf components. Like, an electric motor is a pretty reliable thing. Do we really need to go unwind it and figure that out? Battery technology is pretty well understood. So maybe what we just need to do is see empirical data about your actual flight time and prove that your system acts the way you expect it to, fails the way you expect it to, when you expect it to, and we can certify the control volume of the system as opposed to each and every little bit. Mm-hmm. So I think that shows promise. Mm-hmm. So our interest in that space is great. Then let's get our capabilities on board so that while you're building those hours of experience to share with the regulator to get certified, we're also collecting data and in conjunction can then share that with the regulator and show, hey, here's the real risk vectors in these operational environments and how we should think about evolving our rule sets around detect and avoid going forward.
So just one more question on this, Jon. Thank you. And that is, do you see a world in the future then where we've got a set of standards, a new certification specifically for autonomous aircraft? Then that's all. Yeah, I do. Yeah. It'll be interesting to see how it pans out. I think the challenge is it's become really. I'll never say it's easy to build an airplane, but the tools available have become democratized in a way they've never been before. Yeah. If you have, some reasonable level of technical knowledge and engineering background, you can build something that flies pretty quickly today. So that leads to a widely varying set of flying things. And what I believe will happen is as industry finds alignment with use cases and economic benefit for robotic aircraft, you're going to see an increasing level of specialization of those aircraft to those tasks. I think you won't see what you see in manned aviation today, which is you build a certain category and class of aircraft and you try to make it as generic as possible so that it can fly a number of different missions, right? Like my Cessna, I can take the back seats out and cut a hole in the floor and put a camera in there. I can carry cargo in the cargo bay. I can put the seats back in and carry people from point A to point B. So that was largely, the 20th century world of aviation because it costs so much to design, build, and certify an aircraft that you wanted to maximize your addressable market by maximizing the number of use cases it could do. Well, if you reduce that expense, that non-recurring engineering, if you will, of bringing an airplane to service,
and you can build airplanes pretty rapidly. Oh, okay, well, that flips the economic equation a little bit. Now I can go build a purpose-built flying robot to inspect my pipeline. And that's all it does. It does nothing else. So from the certification point of view, that's an interesting challenge because, boy, I can't really generically put a certification basis out there because each one of these things is doing something different in different operational environment. So it'd be really interesting to see what happens in the global regulatory community. I believe you're going to see more generic approvals on the operational side than you will the aircraft side. I think on the aircraft side, what you'll see is type certification based on your durability and reliability and your operational experience and the data you put in front of the regulator. And then you'll get operational approvals that might be more durable.
Yeah.
Because, well, that's what a pipeline inspection drone does. It's always within 50 feet of the pipeline. It never flies more than this far. If it fails, this is the contingency. And you can start to see how you can basically start to certify use cases and say, great, if that's what you're doing, this is the type of equipment you need. And as long as you do that, go have at it. That's my view.
Would be quite a big change to the way the system works at the moment, right? That would be a dramatic change. So, interesting. If we could just come back to talking about Casia and where is it actually in use at the moment? What R&D projects are you involved with? I know you're involved with. Are you involved with some UTM stuff? And we give some background.
Yeah. So we have been part of the FAA's IPP program for the last couple of years. It's been a wonderful program for us. We were able to get some real world and real use case experience and flight trials, and ultimately got waivers in conjunction with other mitigations for both Alaska and Kansas. We also recently got some waiver approvals from Transport Canada for some work in Canada around power line inspection. We are now part of the FAA's Beyond program. So we're the lead industry participant for the Reno operation, and then we're supporting participant for Kansas, Alaska, and the Choctaw Nation. So those are the environments that we use to take our technologies, get them in the hands of end users, and with the regulator collaboratively exploring these use cases and helping them understand how we might go from today's world of special case approvals into more generic rulemaking, which is really the regulator's goal, right? As they issue these waivers and exemptions, they're trying to learn bits about the edge cases of these mission sets and then use those learnings to inform how they might go put rules on the books so that it expands the number of people that can go do those jobs. So back to your specific question. So that's where we've done most of our kind of field trials, testing, iterations of technology in the use case. We partner with our manufacturing customers. So we have a number of aircraft manufacturers around the world who are purchasing our hardware and integrating it into their systems today. These are the forward-thinking companies that understand that these things need to be tightly integrated now. So as they go through their certification paths, all of the hardware platform is already on board. So you're basically certifying the platform, and then we use software to go enhance the capabilities and enable the detect and avoid functions for their users as they start to deploy the systems in real world use. We have a number of international customers who are, fortunate they live in parts of the world where there's just not a lot of other air traffic. So they don't have the same risks that doing a commercial operation might have in Europe or America, right? So there's nobody else flying. So, okay, great. So your airborne risk mitigation, you can satisfy that with one camera and, there's nobody else around. So go have at it. So we're getting great uptick in, various parts of the world like Brazil, South Africa, some parts of the Middle East. And, that's exciting because every time somebody flies our system, we get the benefit of using that data to train the system and make it better. So every hour that's flown overseas is an hour that helps us share with our domestic regulator and the European regulator more information about the real risks, how the system performs in various environmental scenarios, and then, the time budget that's needed from detection to avoid to make sure that we ultimately do what I said in the first part of this call, which is be the proxy for the human in the see and avoid part of the equation.
Sure. Just another couple of questions, Jon, please. So what's the next big kind of key milestone for the company and the technology, do you think, or is that too general a question?
No, not at all. I think, for as long as we're a company, we will always be investing and developing to increase our visibility, our range of detection, to increase our detection probability, to increase the accuracy of our classification, to increase the accuracy of our range and bearing estimation. So that's the stuff that's on a flywheel that's always part of the company. Where we're really focused right now is trying to ensure that we have as flexible and agile a multi-camera system as we possibly can have, because the nature of these varying types of aircraft that are being built don't really lend themselves to us building a thing that just gets bolted on after you build your airplane. Mm-hmm. So what that drives us to need to do is to be very modular and very flexible in terms of our system architecture, so that manufacturers have options in terms of how they integrate onto their aircraft. So that's a big area of focus for us. And then obviously, you're a testing magazine. It's all of the simulation testing and all of the flight testing that goes into validating the claims that we're making around the performance of our system as a detector.
Yeah, okay. So I think we'll leave it there, Jon, if that's okay.
Great.
It's great of you to take the time out and speak to me. Thanks. If there's thanks. So that was Jon Damush there from Iris Automation talking about his company's detect and avoid technology. And I think you'll agree with me that what an exciting time in aviation it is to have the prospect of these type of specialised autonomous robotic aircraft on the horizon. So thanks for listening, and remember to hit subscribe if you haven't already. Have a great Christmas and a New Year. Stay safe, and the podcast will be back in January 2021. Thank you.